Okay, let's continue. I have a brief announcement first. So the talk after this one, which was about building open source with open source, is actually cancelled. So the speaker had an accident and he will be here with us. But we have a replacement already. So Olaf will talk about Apache BigTalk, which is also building stuff with open source. So it's a very, very nice talk. So just so you know. So now I will introduce the next speaker, which is and okay, it's another talk about machine learning, but this time on database. So please, thank you.
Thank you very much. Well, good morning, everyone. My name is Frank McClellan from Pivotal, and it's really a pleasure to be here this morning with you. Thank you for getting up early on a rainy Sunday morning to join us here. I'd like to speak to you about Apache Madlib, an incubating project that they have now, and the topic is distributed in-database machine learning for fun and common. So I'd like to start with a couple of facts. The first fact is that machine learning and distributed systems can be fun, even for folks who are not necessarily attracted by complexity. People come from various backgrounds to work on distributed systems and machine learning, not just PhDs in computer science. I don't have a PhD in computer science, for example. So folks out there who are looking for interesting projects to work in, I would encourage you to look in this area, either this project or other projects that you learn about here at the bottom. But you still have to earn a living. So fact number 2 is that if you look at every large commercial enterprise out there, they're using relational databases. They're using data which is arranged in relational form in some way, shape, or form. So if you kind of combine, for those of you who don't know, that is the Wall Street Bull. So if you put those two together, this is the equation that you end up with, which is that fun plus money equals Madlib. So that's the area that I'd like to talk to you about today. Right. So in particular, the topics are, I'd like to talk about the journey to Apache for Madlib, because it's not a new open source project. Then look at in database machine learning in a little bit more detail. Talk about the architecture of Madlib. And then talk about R, making R scalable. So Madlib also has R interface as well for folks who are interested in using R. Okay. So let's start with the journey to the Apache Software Foundation for Pivotal. And I'd like to start with a little bit of a history lesson. So this is sort of the history of Postgres as it started in the mid-'80s by a fellow by the name of Michael Stonebreaker, who developed Postgres at US Berkeley. So this is a timeline sort of through to the present. I'll just pick out a couple dates that I think are interesting on this timeline. One that I thought was interesting is that Postgres added support for SQL only about 10 years later in 1995, which I thought was interesting since SQL has been around since the 80s. So in mid-2000, around 2005, there was a bunch of folks at a company called Greenplum who thought about all of that data inside of Postgres. And is it possible to make a distributed version of that, to make a massively parallel processing database which is based on Postgres? So they forked Postgres in the 8.2 version around 2005 and built this massively parallel processing, or MPP engine, on top of Postgres. That was a very interesting and profitable venture for them. About 6 or 7 years later, in 2011, they realized that they had now all of this parallel computing capability within the database, within this MPP database, but they wanted to add a machine learning component to it. Right? So the idea is that you don't want to move the data out of the database operate on it in some kind of external format and move it back in. You want to do everything in database. So that was the advent of Madlib, which was launched in 2011. So shortly after that, with the advent of Hadoop, the folks at Greenplum and later Pivotal said, why don't we take this massively parallel processing engine, swap out local storage and add a distributed Hadoop file system. So take the capabilities of this MPP engine, bring it to the Hadoop ecosystem, and the advent of something called Hawk, which is now Apache Hawk, which you'll hear about later today in this demo from my colleague. So if we fast forward now to 2015, all of these products, Greenplum, Hawk, and Madlib, have continued to develop, both with contributions from the academic community as well as commercial. And these are all open source projects now. In particular, Hawk and Madlib are now Apache integrating projects. So as I said, Madlib is the result of a very interesting collaboration between industry and industry as well as academia. So the project was actually, one of the key people involved was Joe Hellerstein from UC Berkeley. He was one of the first guys who actually thought about in database machine learning, came up with an architecture to realize that. Along the way, we've had a lot of contributions from Stanford, from University of Wisconsin-Madison, as well as University of Florida. So why Apache? Why do we think that Apache Software Foundation is a good place to develop this product? Well, it's because ASF is really a great place to be. It is a place in which developers come together, work in a kind of collaborative way on software in open and productive ways. I think transparency is a really important part of ASF. So if you're going to have an open source project in Apache, you better share what your roadmap is, you better communicate with the community actively, share your technical discussions on the user groups. And if you don't have that kind of transparency, you're certainly doomed as an open source project at Apache. So the other interesting thing is that these technologies are getting so complex right now that it's important for the community to collaborate in order to build them. It's fine for a few folks to be sitting quietly in a room to figure stuff out, but as these projects get more complicated, you want to scale them out and add capability to them, you really need a community, right? So it takes a village to raise a child, it takes a good open source community to build a good software product. So Pivotal has kind of taken that at heart, and effectively all of the commercial products that were developed through Greenplum, including Greenplum Database, the Apache, the SQL on Hadoop product, these have all been open sourced in the last year or so. So all of the commercial data products have been open sourced, including that. Okay, so that's a little bit of a history to Madlib and where Madlib comes from. I'd like to go into a bit more detail on Madlib and talk about capabilities of Madlib as well as the architecture. Okay, so Madlib is about scalable in-database machine learning. It runs in database, as I said, in Postgres, Pivotal Greenplum database, as well as Apache Hawk. And the two kind of key things about Madlib to remember are scalability and performance. So if you have data that fits in memory on a single node, then you don't need Madlib. There's lots of other solutions out there, right? You can use R, you can use scikit-learn, you can use a wide variety of other open source projects. So if you want to do things at scale and very, very large data sets, that's sort of what Madlib is designed for. The other thing is that you want them to be performant in the sense that if you have a large data set and you have a large cluster to run it on, you don't want it to run forever, right? So it needs to be implemented in such a way that even though you're working on large data sets, you get your results back in a reasonable amount. So these are the functions that exist currently within Dlib. As I said, it's a fairly mature library. There's something in the order of 35 to 40 principal functions or principal algorithms within Dlib. It's been developed now over the last 5 or so years. So you see sort of the expected algorithms in the area of supervised learning and unsupervised learning. There's also a number of other support modules. And in fact, this has been a focus of the recent development work, because if you talk to any data scientist, they will tell you that a lot of the time that they spend is preparing the data, doing feature extraction or what have you, in order to input it to a machine learning algorithm. So although like really the focus in people talking about machine learning, they're talking about the algorithms themselves. However, and I think the gentleman early on about Chief Plank mentioned it as well, like a lot of work is kind of getting it ready through code and such. So we've started doing more in the area of support modules. In particular, in the last 6 months or so, we've added a whole host of matrix operations, as well as done things like path functions. And path functions are interesting for finding patterns within data sets. So the features of Dlib are better parallelism. I think that's a key thing. And Dlib it's SQL-based, and it's designed to take advantage of this massively parallel processing architecture in Greenplum database, as well as distributed computing capability within Hadoop. Better scalability, and by this I mean the algorithms scale as your data set scales. So you don't want to change your software as your data sets get bigger. So if you have a small data set, you can do development on your laptop, on Postgres, for example, and then you can run that as well on, say, a hot cluster with 100 nodes. And the software hasn't changed. It's the exact same software that ran on your laptop that's running on a 100-node cluster. Another key thing is predictive accuracy. If you speak with data scientists, they don't like to sample data, right? Even if it's very large data sets, especially if you have dimensions with high cardinality, like user IDs and things like that. If you want to group by those, machine learning by user ID, then even if you have a large data set, if you sample it, you can end up with sparse data. So the idea is to operate on all of the data. So these are the supported platforms. As I mentioned, both Hawk, Greenplum database, Postgres, they're all open source. So scalability. I have a couple of charts on scalability here. The way to read this one, so this is sort of scaling by cluster size, if you will. So on the x-axis, you have number of independent variables, and then on the y-axis is the execution time, right? So this is for linear regression on 10 million rows, and you can see in the top right-hand side there, if you have 6 segments of worker node, it takes about 200 seconds. If you double the number of segments, so you come down to the red dot on the right, you can see that execution time is approximately half, about 100 seconds. If you double the number of worker nodes again to 24 worker nodes, then again your execution time is halved as well. So this is just to show you the linear scalability with cluster size. With respect to regression, with respect to scaling by data size, This shows linear regression scalability for 10 million, for 1 million, 10 million, and 100 million records. You see that it's linear, both on green palm as well as on Hawk. This is logistic regression, scalable, again, linearly. So this is what the example usage looks like. So it's SQL-based, as I said. So it's a declarative call within a SQL statement. So this is how you would train a model, for example, for linear regression. Here I'm predicting the price of houses, given some historical data on houses, including how much is paid in tax, number of bathrooms, and size, for example. So I train that model. Then if I want to do a prediction, I take the result from that, and again I call, and again within my SQL statement, I do a prediction, based on the result of the training. So it's fairly easy to use. Then I'd like to talk to you a little bit about the architecture. So many machine learning problems are iterative in nature, and the architecture with the way it's set up with Madlib is that it's a combination of Python and C++. So we have this high-level iteration controller layer, which is written in Python. The actual core algorithms themselves are implemented in C++. Right? And there's a C++ extraction layer to the database. The database is already. So to look at how scalability would work for, in this case, linear regression. So each algorithm needs to be kind of crafted for a distributed environment. As you guys probably all know, that you can't just take an algorithm which is written for a single node and automatically have it distributed. Right? You can't do that. So when you're developing a new algorithm in Madlib, you need to think about how to take that algorithm and distribute it across, decompose it so it can be distributed across multiple different nodes. So we take kind of a classic linear regression example. Think of it as sort of, straight line fit through a set of data with higher dimensions than that. And we want to find essentially C, which is we want to find our slopes, if you will. So the way you can solve that is with ordinary squares. Equation looks like this. So when you set up your matrix X, you want to kind of distribute your data. So you think, well, why don't I go ahead and distribute it like this? I'll put A and B in worker node 1, C and D in worker node 2. If I do the transpose, then A and B in worker node 1, C and D in worker node 2. And then I start doing my multiplication. What I see is that I'm actually operating across segments here because A and C are in different segments, right? So that's going to increase network traffic. So I don't want to do that. I want to reduce the amount of network traffic I have between worker nodes. So I need to kind of rethink this problem. So if you kind of look at the algebra, you can see it's actually decomposable, right? You can see A squared, B squared, and AB kind of, you could separate those out, and you could do every operation on those in one node, all the operations on C and D in another node, and then just collect them after, right? So it turns out you can do that using something called like an outer product as opposed to an inner product. And the idea then is that you can see all of the operations on the left-hand side of the second line could be done in one node. All the operations on the right-hand side could be in another, done in another. So this is kind of the way that we think about decomposing machine learning algorithms for distribution in an MQP environment. Same kind of idea for the second term here. You can decompose that to do operations in segment 1, segment 2, or any number of segments. Bring them together onto a master. Okay, let's skip ahead a little bit through this. not every data science speaks SQL. So many data scientists use R. So what we've done is built an R interface for Madlib. So what it allows you to do is use familiar R syntax on your client machine, but have it actually call this distributed MVP database in the back end in order to do scale out R. So the way that works is that you write regular R on the client, that converts it to SQL, it executes in the database, that's where the data lives, and then it returns the result set back to the client. Right? So the big data, if you will, is in the database, and the result set comes back to the client. So just to finish up, so what's coming up, we have our 1.9 release, which is coming up within the next month or so. The areas that we focused on here is we've completely refactored the support vector machines, including support for nonlinear kernels. We've added more in the area of utilities, as I mentioned, matrix operations, path functions, stemming, and some other text analytics kind of functionality. And in the future, there are some potential areas that we're very interested in working on. A lot more in the area of utilities, a bunch more predictive models, including those listed here. And in terms of usability, thinking about Python API as an example for 2.0 release. So thank you very much for your attention. You're more than welcome to participate in the project. Here's some links for the website, where the software is on GitHub, and the mailing lists. Check it out, and if you have any questions, send them to the mailing list, and we would be happy to respond. Thank you for your attention.
That's time for a couple of questions.
Is it true that the database server must be the same that the computing server, or can you use a separate?
Sorry, could you please repeat the question?
Okay. So in one of your last images, you said computation is carried out in the database server. Right?
Yes.
And so it must be the same server. Right? Can't have the database server and the separate computation server. It's different hardware. Doesn't make more sense.
Yeah, so it is the same. Like the computation happens within the database, and the data is stored in the database. Yeah, so that it is actually in the same structure.
Any other questions?
Anyone wants a t-shirt, let me know. Until they're gone.